And I think if you were in the general session this morning, you saw in the investment column and what topics were getting invested in versus divested, encryption or security data breaches was one of the few that was having encryption or having an increase this year. And so if we look at a history over the last 10 or so years of how many incidents there are, you can see anywhere from 300 to 600 to 700 incidents a year. This is statistics from a website that tracks these. It's dataprivacy.net. Now 2015 here looks pretty good. Of course, these statistics fall behind, and this is probably 4 to 5 months old. And there have definitely been some big ones in the last, even in the last 3 weeks. I think there was a big one with T-Mobile losing a bunch of customer data. So these are on the rise. Now IBM sponsored a presentation, or excuse me, sponsored a research study on the cost of data breaches and what it does to companies. And it just looked in 2014 for what the costs were, and it studied across a number of countries and a number of companies. And you can see here that you have varying statistics, but these numbers, like $3.8 million per data breach, is not insignificant. And when you look at the cost per record, Germany and the US are the two highest in the world at $200 a record. So if you go back and you look at Target or you look at Home Depot, where they had a loss in the range of millions of records, you can do some math and see that $3.79 million is not the cost that it was to Target or to Home Depot. So if we want to worry about keeping our data secure, there's really 4 things that we need to keep track of. The first is data encryption. The second is network encryption. We need to watch access control, and we need to keep track of auditing. Now this presentation is focusing on data encryption, or excuse me, on encryption. So we're only going to talk about the first 2 of these. We're going to talk about data encryption and network encryption. But I don't want you to forget that access control and auditing are there because they're absolutely critical. So let's set the stage and talk a little bit about encryption and what it is. At its heart, encryption is a mathematical algorithm. You take something that you want to hide, say my secrets, which is called the message. You take a key like this, you apply the Cipher function, and out of that you get ciphertext or encrypted data. Now the point of doing this and how this applies to data breaches is no encryption is perfect, right? What we want to do is we want to increase the amount of time if someone were to come across some data. We want to increase the amount of time it takes them to get any use out of it. So with encryption, there are a number of different kinds of Cipher algorithms. There's the good old substitution algorithm, which is something maybe we played at with kids as we were kids. If you remember this silly little decoder ring, you could just spin it and know that A is Q and B is X or whatever, but that's not particularly secure. When we're talking about real encryption, we look at symmetric encryption algorithms and asymmetric algorithms. So with a symmetric algorithm, what that means is you have a single key that is used for encrypting and decrypting your data. And you can think of this a lot like a house key, right? You have one house key that locks your door, and you have another, the same house key unlocks your door. There's a few common algorithms. There's the DES algorithm, which was created in the late 70s. It's not particularly secure. The government, the US government, excuse me, came up with an idea to use multiple keys and re-encrypt the data to come up with this standard called triple DES. That is also a little bit old, and the current standard that the US government recommends is AES, or Advanced Encryption Standard. Now, if we go back to asymmetric algorithms, what you have here is you have 2 keys that are mathematically related, but one works to encrypt your data, and that's called the public key. And you have one that decrypts the data, which is the private key. Now, what this is useful for is you can distribute the public key freely because people can encrypt data. It's available out there. And if someone has this key, it's not going to give them any ability to see your data. The private key, on the other hand, is one that you need to keep a hold of, since it will decrypt. Now, algorithms, RSA is the most common algorithm that's out there for asymmetric encryption algorithms, but there are definitely some other ones that are on the rise. Elliptic curve encryption is a new one. I'll mention that briefly later. That was discovered by IBM in the, I think, mid-'80s. But this encryption is used primarily in tools that you may have used, like SSH. It's used to authenticate servers between the machines, or PGP if you're encrypting email, sending it back and forth. So the key length is something that's extremely important when we're talking about encryption. The more bits that you have in your key, the more secure your algorithm is going to be. Now, we'll talk about asymmetric versus symmetric encryption algorithms and the different sizes, because all bits are not created equal, and it's a function of what kind of encryption algorithm that we're using. So from asymmetric versus symmetric, the big difference between these two is that symmetric encryption algorithms are much faster, orders of magnitude faster than asymmetric ones. And so if we look at the number of bits that are used to provide a relative the same amount of encryption, or the same level of encryption, you can see here that a 128-bit symmetric key is roughly equivalent to a 3072-bit asymmetric key. And so when we're looking at this RSA encryption, you may ask, it's used in all kinds of things that we're familiar with, but you don't want to use it for database encryption because it's too slow. Now, I mentioned before asymmetric or the elliptic curve cryptography. That is significantly faster. It's asymmetric, and you can see here that the bits required for the elliptic curve cryptography are much closer to what we get with symmetric encryption in terms of performance. And if you look at just like raw performance in terms of these two asymmetric algorithms, we're talking like a 10 times speed up in these. So this is definitely something that's coming in the future. So let's talk about key management. The key that you have to encrypt your data is, of course, very important. And if you lose that key or it falls into the wrong hands, you have a problem. So like a password that you use to log into your servers or connect to your database, you want to change it on a regular basis, right? So unlike your password, you don't get this. You have to put policies in place within your organization to make sure that you change your keys regularly. This would be like if you think about your house. If you lose your house key, someone finds that you don't want them walking into your house, maybe you change your locks. But there's a downside. If I'm going to change the locks in my house, I actually have to go and change the locks in my house. I can't just change the key. And it's the same thing with encryption. If I encrypt my data and I want to use a new encryption key, I have to decrypt the entire thing that I've encrypted and then re-encrypt it using the new key. Now, if we're talking about an email, not very much data, not a problem. If we're talking about a 10 terabyte data warehouse, that's a little bit more involved. So how do we get around that? There's a common paradigm in encryption called key wrapping. And so here we have an encryption key, and what we're going to do is we're going to encrypt that encryption key using a second key. So we have a master key that we use to encrypt the encryption key. It's stored separately. You would keep it in some other location, and it eliminates the need to re-encrypt. Because when I want to change this master key that I'm using, all I have to do is decrypt the encryption key and encrypt it with a new key. And this encryption key is small, so it doesn't take very much time to decrypt it and re-encrypt it using a new master key. Does that make sense?
I don't follow that logic because I want to break the raw data. And the raw data is encrypted by the base key, which you do not change. So I have more
Right, so the question was, I want to get to the data. I don't care just about the encryption key. Well, so the question here is that the encryption key is encrypted using a different kind of encryption. So if you wanted to get to the raw data, first you need to decrypt that encryption key, and then with that encryption key, then you could go and decrypt the rest of the data. So we're really interested in protecting that encryption key to ensure that it doesn't fall into the wrong hands.
Can I not run a brute force attack if I know, for example, a subset of the data? I can just brute force all the keys and then find the encryption key instead of the master key that encrypts the encryption key.
That's true. So the question was, can I not just brute force it? And that's the whole reason why I mentioned with the key size is extremely important. If you have a very small key, it will be relatively quick. Or if you're using a poor encryption algorithm, it'll be quick to break that. But with, say, AES 256, or as I'll mention in a minute, with these asymmetric encryption algorithms, if you're using a significant key size, it could take years to be able to decrypt that key. So when I was talking on that slide about the sizes, I think what the US government says is a 128-bit AES key is good if you need your data to be unbreakable by 2030, so 10 or 15 years, right? If you want something that's encrypted, that's resistant for much longer than 10 or 15 years, then you would say go to 192 bits or 256 bits. Or roughly the equivalent if you're looking at asymmetric encryption. Oops, sorry. Okay, so now with that basic talk about how encryption works, let's talk about encrypting data at rest. So I showed you this graph before showing the data breaches. If we break it down into what you're going to worry about when you have data at rest, that's basically losing a device, right? So it could be someone leaving a laptop in their car and it being stolen, or it could be someone getting into a data center and pulling a hard drive out of a server. That was actually one of the things that happened in one of those companies that I showed earlier. Or it could be something like a hard drive isn't recycled properly when it's replaced. So these small sections here are what we're really trying to avoid with encrypting data at rest. And so if I just rescale this, I'm going to break it down even further to stationary like servers or portable devices like a backup tape or a laptop. And you can see what we're working with. So there's two levels that we can look at encrypting data at rest. We can do it at the system level. And some of the options we have here are AIX and its encrypted file system. That's included with AIX with your license. It's not an extra charge. But it's a little bit complicated to implement. It's supported with DB2, but the challenge here is that AIX file system encryption works at a file level, so you have to encrypt each individual file. And you can think about the database, if you think about the tablespace files, okay, that's not so bad perhaps. But then when you start thinking about transaction logs and other files that DB2 leaves around in the file system, it becomes a little bit of a challenge. Now, you can set up policies for directories so that they inherit various encryption policies, but you don't have control over the data in the same way. Because if a DBA or a junior DBA or a system administrator says, oh, well, these log files, they need to be moved somewhere else because we're running out of space, boom, all of a sudden you have not encrypted data anymore. So another option is Infosphere Guardium data encryption. This is an add-on product to the system. Now, the nice thing about this is it provides a centralized management or policy management system where you have a server that's sitting in an enterprise that stores keys and enforces policies. The servers, for example, a database server would have an agent that runs on it that talks to the central server to get keys, change keys, and enforce that. But of course, it's an add-on product. Now, if we also think about cloud providers, you can look at the various cloud offerings, and you'll see that when you create a volume, you have the option to create an encrypted volume. There's varying key management. Some of this stuff is not particularly transparent to us in terms of how the encryption works. And I'll also point out that this is not something that the lab has certified, at least publicly as far as I know. So then we can look at database level encryption options. Now, these two UDFs have existed for a long time in DB2, at least since version 7, maybe since version 5. And while it's possible to use them, I would strongly caution against it. The encryption algorithm is very old and not particularly strong, but then the biggest challenge here is that this is a UDF and you provide the data you want to encrypt and the password in the UDF call. So where is that password stored? It's stored in an application program. Users may have it for executing SQL statements. And even worse is a single, you may use one password for one row of data, but you may not use it for the next row. So you can't even necessarily decrypt everything if you know one password. You could have 100 passwords. So now the other option, which I'm sure you've all been waiting for, is DB2 native encryption. This is a feature that was announced in DB2 10.5, FixPack 5. I know that the lab says that they don't introduce new functionality in FixPacks, but yay. This is a feature that is included in advanced editions, so Advanced Enterprise Server Edition and Advanced Workgroup Server Edition, and extremely smartly of the marketing folks, it's included for free in Express C. So you may say, okay, well, what do I want to do if I have Workgroup Server Edition or Express Edition? Well, IBM answered that with this DB2 Encryption Offering, which is an add-on license that you can purchase. And if you look, sorry if this is a little hard to see, you have these features that are, once again, back in the DB2 LIC-M output with the DB2 Encryption Offering that you can add on. So it gives you a cost-effective way to get encryption without having to go all the way up to the advanced editions. So what does native encryption do? Well, it encrypts all your online data. It is transparent to applications. Once you've encrypted the database, there's no changes that are necessary to the applications. You don't have to recode anything. It just basically works. It's some database administrator work to get it implemented, which we'll talk about, but then you're ready to go. One of the nice things is it was written to take advantage of hardware encryption. So if on Intel servers you're on relatively new Xeon chips, you can take advantage of the hardware acceleration there. Or if you're on Power 8 hardware, you can take advantage of acceleration there. Some of you may note that Power 7 has hardware assist for encryption, but because it's done at the kernel level and not at user level, DB2 isn't allowed to take advantage of it. So we talked about before this concept of key wrapping, where we had an encryption key and a master key. And so this is what DB2 does. We have a data encryption key, which is used to encrypt all of the data in the database. Right? You can choose two different Cipher algorithms, the triple DES or AES, and then you have options for your key length. Now, that data encryption key is then encrypted with another key. It is stored in a key store that is encrypted with a password. We'll get into that in a minute. And that's the master key that you can choose to rotate on a regular basis. So what's encrypted? Tablespace data is encrypted, all of your transaction logs, and of course the archive logs that go along with it. And something that most people probably wouldn't think about is dump files, right? When DB2 dumps stuff out into the SQLib DB2 dump directory, oftentimes there will be binary data included in that maybe you don't want to have people find. So that gets encrypted as well. From a service perspective, I think the lab can provide options to help decrypt that data if you need to send dumps in. Now, backups are also encrypted. So when you encrypt your database, by default, DB2 will go and set up the system so that all backups going forward are encrypted as well. Now, when you take a backup, the data encryption key for the backup itself is different. It's not the same encryption key that's used for the database. So basically, in this case, you're re-encrypting data on backup, but you have options to specify different ciphers and different algorithms for the backup than what you're using for the database itself. So how are we going to do this? I made a little roadmap here for you that shows you the steps that we're going to go through, and it's going to depend on whether you have an existing database or a new database. Now, the encryption library that DB2 uses is something that IBM produces called GSKit, and there is a very nicely named utility called GSK8CAPI-CMD. And if you're running on a 64-bit system, you get to add _64 to that. Now, I don't want to type that a million times every time I have to do something with the key store, so I'm just going to create a nice little alias to make it a little bit easier. So the first thing I'm going to do is I'm going to let GSKit generate a password for me. I can use this -random and -create. It gives you something nice that's simple to make sure you have a secure password and not something like 1, 2, 3, 4, 5. Next, I'm going to create a key store to store that data. I'm going to provide the password here. I'm going to specify that I'm going to stash the password, and I'll get to that in just a minute, but what that means. But where I'm going to put this now is I'm going to put this in the SQLib security directory. Now, I don't know if that's the best place to do it. It makes the most sense logically to me. You could argue that because DB2 owns the SQLib directory that maybe that's not the best, but I think that from a conceptual perspective, it's easy to store it there and keep it there. You'll see also here I'm using an environment variable just so that the file itself will have a name with the DB2 instance owner. So if I go and I look at what was created there, I see I have db2 inst2.p12, which is the new key store, and then I have this .sth file, which is a stash file, which I'll talk about in a minute. So now I'm going to update the database manager configuration file to tell DB2 where to look for the key store and what kind of key store it is. Currently, the only key store type that DB2 supports is this PKCS12, which is what we used when we created the key store here. I think you can look into that and see that perhaps in the future there may be other key store types that are allowed. Now, I just want to call out this one thing here. I'm typing this command on a command line, and what happens when you type a command on your command line? It goes into your shell history. So maybe that's not the smartest thing to do here. So be aware of when you're doing this, if you're going to type your command, if you're going to put passwords on your command line, that maybe you want to go back and cleanse your shell history in the future. Okay, so we've done this. And now if I go and I look at the database manager configuration just to verify that I've set these things, you can see here that they're set. So now I'm going to create a new database. Now we're in Dublin. Maybe U2 wants to create some encrypted data. So I'm going to create my database, U2DB. And that's it. With a new database, it's that simple. You add the encrypt option to the create database statement, and DB2 will automatically use AES 256 encryption. You can see here I get the database configuration, and I'm just looking for ENCR to get all the configuration parameters that apply. You can see here that the database is encrypted here, and DB2 has conveniently gone and set these two options, encryption library and encryption options, for you so that backups going forward will be automatically encrypted. You can see here the cipher and the key length and the mode for the cipher. So now let's say I have a database that already exists and I want to encrypt it. Well, the way to do that is through a backup and restore. So the first I'll do is I'll back up my unencrypted database, and then I get to do my favorite job ever as a consultant. I get to drop the database. Now, I don't know if that's something crazy about me, that my most favorite thing that I never get to do is drop a database, but there's some awesome power in dropping a 2 terabyte system or database. So I'll drop the database, I'll restore it, and guess what? There's only one command line option that you need to add to your restore statement, encrypt. DB2 will then restore the database, apply the encryption to the restore as it's getting written out to disk, and when you're done, again, same thing. Database is encrypted, and DB2 has set your encryption options at the database manager configuration. Now, the key store holds your master key. And if you lose that master key, you're going to have a really hard time getting at your data. Right? We talked about that before, where decrypting the encryption could take years. So you really don't want to do that. So it's absolutely crucial that you back this file up. Now, there's 4 times when an encryption key is added to this key store. So each of these 4 cases here are when you want to make sure you take a new backup of that file. Now the stash file, I mentioned this before. What the stash file is it is a file that sits alongside your key store and allows DB2 to access that key store without knowing what the password is. It's obfuscated and stored in here, so keeping control of this file is important. It's like I said, obfuscated, but it's something that you want to make sure that it's not really falling into the wrong hands. That is something of a little bit of a concern, perhaps, for encryption fanatics. It's not a mandatory thing, and we'll talk about that in a few minutes.
I think we should make it more open. If someone has access to both the stash file and the key store, can access that the key.
Yes, exactly. That's definitely, so the comment was, if you have access to both the key store and the stash file, you have access to all the encryption keys. And that's exactly an astute comment. That's why when I mentioned early at the very beginning of the presentation, access control and auditing are extremely important. That's what we're talking about here. So if we want to get some information about the master key, there's a nice handy function called admin get encryption info that you can execute as a SQL statement. So here I'm just going to find out what the master key label is. And this is a system-generated one, and this is the format that DB2 uses when it creates a master key for you. Just, has instance name, database name, and the date when it was created. I can also, from that same function, I can find out when the key was rotated and who did it. I split this into 2 calls just for formatting purposes. There's a whole bunch of additional information that's available from this table function, so it's worthwhile looking at what else you can find from it. So if I want to rotate the master key, this is extremely simple. There is a nice function, another function called, stored procedure called admin rotate master key. So I'm just going to call this. I'll provide null as the option for it, and it will rotate the master key. Now, I do want to call out this null. If you look at the documentation, normally what this parameter is meant for is a key label. And if you read the documentation, you'd think that, okay, I'm going to give it a name for a key label, and DB2 will use that name when it creates the new master key. That is not how it works. You have to have a key already existing in your key store if you want to specify the specific label of that key. And I'll show you in a few minutes that that's a little bit complicated to do. So by using null, you'll just get another system-generated name. If I execute that same function to see the encryption information, you can see that I guess Bono was fooling around in the system and decided to rotate the master key like a smart database administrator. Okay, so backups. So when you're backing up your database, you're just going to add the encrypt option, similar to restore. It's a simple thing. Like I said before, the backup DEK, or data encryption key, is unique each time you run a database backup. So you re-encrypt the data every time you do the backup. For doing encryption, and if you are using compression, you have to be careful how you do that. Because if you compress your data, if you encrypt your data first and then you try to compress it, you're going to get terrible compression, because the whole point of compression is you're trying to find common strings that you can eliminate. So if you encrypt it first, you have just basically effectively random data, and you're not going to get any encryption whatsoever. So it matters that when you want to compress and encrypt, you have to compress your data first and then encrypt it. So IBM provides a library that you can use for this function called libdb2 compression encryption. And you can specify that. You can change your database configuration to use that, to specify that if that's what you want to do as a default. Now, one thing I'll also mention is if your source database isn't encrypted, you can still back up and encrypt your backups. So if you have a highly secure system, maybe it's not connected to anything to the network, it's just sitting in some room like in Mission Impossible, but you're going to send your backup tapes off-site, you can encrypt your backups without worrying about encrypting your database. So now let's say we want to send some backups to a third party, and this is a case where you would want to use a different encryption key. What I'm going to do here is I'm going to create a key. Now, strangely, the GSKit utility does not provide you the ability to create a key, at least from the utility. DB2 is obviously calling some kind of internal API, but the GSK8C API command can't do that. So I wouldn't recommend that you actually do this because you're kind of dependent on how secure this dev random is, but I'm just going to read 32 bytes out of dev random to generate basically a 256-bit key. And I'm going to store it in a file here called /temp/third-party key. And then I'm going to use the gskit command to import that key into my key store. And I'm going to give it a label because in this case, let's say Bono wants to collaborate with Sinead O'Connor. So I'm going to create a special master key in here for Sinead. Now I'm going to back up my database again, but to specify this different encryption key that I want to use, or the different master key, I'm going to specify this encryption options here, master key label equals Sinead master key. Now, one caveat to this is that if you remember earlier, I showed you the encryption options get set by default when you create a database. If those are set and you try to do this backup just like this, it will fail because bug, perhaps. So you actually have to go and you have to unset the encryption options in your database configuration in order to do this. I'm assuming this is something that's probably going to be fixed. So now, what I have after I've completed that is I have an encrypted backup that I can just post on the internet for Sinead to download. But then I also have this master key that I created that I need to get to her so that she can actually decrypt that backup. And that's something that you don't want to do. You don't want to just email it to her or post it on the internet. Maybe Bono's going to go and meet her at the pub and give her a USB drive or something. So get that information to her in a out-of-band or more secure manner. So what she will do then is she will just restore this database, right? She will take the backup, run restore. Now you have to encrypt the database. If you have an encrypted backup, you cannot restore it and not encrypt it. You have to encrypt it. So now the stashed password. We talked about that before. It's a convenience thing that's available for you. But if you're particularly concerned about security or you don't think that you can control who has access to your servers, you can not use the stashed password. I mentioned before, even if you lose this file, it's not that big of a deal as long as you know what the password is. So here, I'm going to start the instance, I'm going to start DB2. And if I try to connect when I don't have the stashed password file, it's going to fail because DB2 can't open the key store. Now, what I can do is I can just tell DB2 to open it. I can run DB2 start again. There's a new function called open key store. It's not going to hurt the system if the instance is already running, and it will just prompt you for the password. Again, this is something where you could actually put the password on the command line. Probably not the smartest idea. So it prompts me for the password. It just gives me this message that DB2 is already started. But now, if I try to connect to the database, it works fine. If you have an instance that has both unencrypted and encrypted databases, if you start the instance without a stash file, then DB2 will work. Your unencrypted databases you can continue to connect to. Your encrypted ones you won't be able to until you provide the password. So we talked about those 4 cases when you want to make sure you take a backup of the key store. You can look in the DB2 diag log. DB2 helpfully gives you this message, this error 8014W. So if you use DB2 diag to search for it, you see this nice little message, hey, back up the key store. So that's a good thing to add perhaps to monitoring to look for that command to make sure that backups are occurring if you're not automatically backing up the system. If I want to see what keys exist in my key store, I can use this gsk8 command with the stashed option, and I can see all these various keys that are in here. DB2 will not remove keys from your key store. That may not be a concern, but if you're particularly OCD like some DBAs are, maybe you want to delete some old master keys when you have no need for them anymore, and you can, again, use this gsk8 command to delete the keys. And now you can see I deleted Sinead's key because she was not being particularly helpful to work with. So that's encryption of data at rest. That is one of the keys of ensuring that your data is secure. The next, of course, is encrypting data in transit. And data in transit is when you're talking between a database client and the database server. If you're on an open network, someone can just basically look at the data going by, and having your database encrypted is not particularly helpful. So we saw this graph at the beginning showing all the breaches. If we look at the data breach incidents that would fall under this encrypting, or where encrypting data in transit will help, we have a small number here, whether this is from disclosure or hacking or whatever. So what are our options here? For a long time, since at least version 9.1, IBM has supported these two options for the authentication database manager configuration parameter. You can set server encrypt and data encrypt. Server encrypt uses just encryption for the username and password when it's getting sent over the wire. Data encrypt encrypts all the data. Similar to what we saw with like some of the older UDFs in DB2, these are fairly weak encryption and you don't really want to use them. So what we want to use is SSL. Now SSL, you guys, I'm going to have to speed up a little bit. SSL, you probably are aware of it from a web browser. It's a encryption method across the wire. You use a public key algorithm, so you can distribute basically a public key out to anyone, and then the server authenticates with that. With public key encryption, you have the concept of a digital certificate, which is designed to ensure that a particular private key and public key are a pair. So that when you get a private, when you have this public key, you know who it actually belongs to. It's certified by some authority to do that. So if we're going to set up SSL encryption on the server there's two parts. We have to set it up on both the server and the client. So on the server, similar to what we did with data at rest, we're going to use the gskit command. We're going to create a password, and we're going to create a different key store than we used for the data encryption. The reason for this is this has been around for a while, and it uses a different format. So I'm going to create this database. If you really get into command line options, you'll notice that the type here is different. So I'm going to store this in the SQLib security directory. This time I'm going to give it this -SSL file name just for identification purposes. And you can see now I get a key database and a stash file. And like before, if I have this password on the command line, it is a wise choice to make sure that you clean out your shell history. Next, I'm going to create, in this case, I'm going to create a self-signed certificate. Self-signing allows you to basically have your own certificate authority. You become your own certificate authority. So I'm going to go ahead and I'm going to create a server certificate that I'm going to use here, and it's going to get added to this key database. And then I need to extract part of this key to distribute to my clients so that they can basically know that the server is who it says it is. So I'm going to create this file here, mydb server cert, which you'll see in a few minutes.
Some companies have a policy to only use verified certificates, for example. Can I import those?
So the question was, some companies have a policy to only use certificates that are created by recognized certificate authorities, like VeriSign. And yes, of course, you can import those without having to use a self-signed certificate. So now I'm going to set 3 parameters at the server level to enable this. I'm going to point it to the key database. I'm going to point it to the stash file, which is a little bit different. You'll notice you have to actually tell DB2 where the stash file is. It doesn't make an assumption like it does with native encryption. And then I have to set the server label so that the DB2 knows which particular certificate in that key store you're going to use. Next, I'm going to set the SSL service name, database manager configuration parameter, which tells DB2 which port to start the SSL listener on. And then finally, I'm going to update the DB2 COM environment variable to add SSL to it. Now, you'll notice here that I have TCP/IP and SSL specified. This is not particularly secure because it says, OK, if you want to use SSL, OK, but if you want to not use SSL, you're free to. So this is probably not a great idea if you're really concerned about security, but I mention this only so that you're aware that as you transition from non-encrypted to encrypted, you have the option to have both listeners running. So that's it on the server side. On the client side, again, this is going to depend on what kind of client you have, whether you're using the data server client or you're using a lighter client or Java. So for the data server client, I'm going to create another key store to store that server, the certificate that I extracted after I created a self-signed one. I'm going to add that to this key store and update the client configuration parameters. I'm going to then catalog my database pretty much as normal. The only difference here is, of course, make sure I use the correct port, and I'm going to specify security SSL in the catalog TCP/IP node command. I then catalog my database. Oh, question?
And then slide before, inside Windows, I can use the Windows certificate store.
I don't think that DB2 is integrated. I don't know the answer to that, actually. Whether DB2 can actually read from the Windows certificate store.
I think so.
Was that recent addition?
Yeah.
OK, thank you. OK, thank you. OK, so then catalog my database. Catalog database command is no different. And now I can connect to the database, and it's going over SSL now. It looks complicated, more complicated than it is. If I'm doing from a Java, you have the same kind of idea, right? You have a key store. It's just created differently in Java. You use this key tool command, but you import that same server certificate into that key store. Now, when you do this, you're going to have to provide a password for the key store. This starts to become a little bit of a challenge because the password may be different all the time, and you don't have a stash file with Java. Oops, excuse me. And Java, actually, when you import it, it will ask you to verify some of the details from that certificate that you're adding to the client key store. So once you have this, now you have this file here, this Java key store file that you're ready to go. So in your application program, you're just going to set a few system-level parameters to point the Java application to that key store. And now you actually have to give it the password, which you're going to store somewhere in the code. Once you've done that, you're going to just basically set your connection properties and go. It's pretty simple. The only difference that you're adding here is you're adding this SSL connection property to your standard Java properties. For ODBC and CLI clients, you're able to connect by specifying a DSN directly in the code. And so here, it's basically your pretty typical DSN. Obviously, the port number is going to be different, but you're going to add these couple of commands. You're going to add this SSL security, and then you're going to add the key store and key hash that you created when you created those key store with the global service kit or GS kit on the client. Now, I'll add here one oddity about this. This is Ruby code, but one oddity here is you specify the username and password in the DSN instead of in the connect statement. I don't know why this is. This may be a programmer failure on my part, but in this case, to get this to work, I had to specify it in the DSN and not in the actual connect statement. So just a couple of quick gotchas about SSL. Certificates expire. So if you you need to keep track of that, and if they expire, you're going to have to kind of go through this whole rigmarole to distribute that certificate out to clients if you're using a self-signed certificate. If you're using a certificate that was created by a recognized authority, recognized certificate authority, you save all the client modifications that you have to do. But just for reference purposes, this is the error that you will get if you try to connect to the database and the server certificate is expired. You get this error code here, and this is a nice link that gives you all the possible error codes that you can get from GSKit, but they're not particularly obvious. You just get this normal SQL 30,081N error. So a couple other network considerations for encrypting data in transit. HADR is not encrypted. HADR traffic is just unencrypted across the wire. So if you want to ensure that that is secure, you need to look at something like a VPN between your primary and standby server. The FCM, if you're using DPF, is another network area that's not encrypted. This is perhaps a little bit less of a concern because typically you're dealing with a private switch, and if someone has access to go walk up into your data center and plug into a switch to look at switch traffic, I think maybe you have more problems. And again, that falls into that access control area that you want to be aware of.
How about application like QREP and CDC?
So I can't answer that question. That question has come up before as to whether QREP and CDC are able to read the logs. And I would imagine that there has been some work to allow the APIs that they use to read the log files to do it. But I know, for example, like there's a HADR utility that allows you to monitor or analyze your log files, and without any updates, it was unable to read the log files as they were encrypted. So I would imagine there would have to be an update to QREP or CDC to enable that. Okay, so in summary, we talked about various encryption algorithms and how they work. We talked about key management, which is absolutely crucial. We talked about how to encrypt your database and what kind of options you have. And we talked about how to encrypt your data in transit from between the client and the server. But like I said at the beginning, there's two more keys that are extremely important if you want to ensure that you have data security, which are access control and auditing. But we don't have enough time to talk about that today, so you'll have to look for that in a future presentation. I just want to call out one quick thing, if I can make a plug. Fred in the back there and I run a podcast about DB2 LUW stuff called The Whole Package Cache. We'd love for you guys to listen to it if you want to spend 30 to 40 minutes listening to us jabber on about various news in the DB2 world. And that's it. Any questions?
Yes, is it possible to encrypt only some table spaces? Only the whole database?
Native encrypt, so the question was, can you encrypt only certain table spaces in a database? And the native encryption feature, as it currently exists, is only, it's all or nothing. Yes?
Is there a certain assumption about the overhead it takes to decrypt and encrypt data?
So the question is there assumption about the overhead? So from a performance perspective, one thing you have to consider is that encryption occurs at write and read to disk. So when the prefetchers are reading data off of disk, they do the decryption there. The data in the buffer pools is unencrypted, right? So it's when you're reading data into the buffer pools or writing data from the buffer pools out to the logs or to the files that occurs. So you have to be careful with performance here, and you want to ensure that you're trying to minimize, reads and writes just as you normally would, but it becomes more important with the encryption feature. But of course, if you have hardware that allows you to leverage some of the hardware assist, it's going to cut that down. Now, on a database backup, you're going to definitely see a bigger penalty in terms of performance because you're reading and writing basically your entire database or portions thereof. So that's where you're going to see the pain.
You mentioned Java property files and the DNS, and they both had embedded passwords. Is that part of your access management where you have to make sure those things are hidden and secure somehow?
So the question is about storing passwords in application programs. And that's kind of outside of the scope of this, but yes, obviously you need to have very good controls in terms of passwords for how your applications are getting them and where they're storing them. Anything else? All right, thank you very much.